Hi, everyone. My name is Shalini Ghosh. I'm going to talk here today about learning better representations for automated speech recognition. I'm sorry that I could not be there in person today due to some unforeseen circumstances, but you can find me on LinkedIn and happy to answer any questions offline. So this is my background and some of the work that I've done in multimodal representation. In the past years. So currently, I'm a principal research scientist in Alexa AI in Amazon. And right now I was focused on speech, NLP, but also in general, I work on learning multimodal representations that can improve individual modality as well, especially if you learn representations from text and audio and images. And previously, I've also been a director at Samsung Research America, where me and my team worked on a variety of video processing problems, processing video in multimodal way. And then I've also been a principal scientist at SRI International for almost a decade, actually for more than a decade in my life. And I've also been using text and image representations over there for various kind of tasks like visual question answering. And also, I've also been a visiting scientist at Google Research, where I worked on how to improve text-based representation using contextual information. So in short, I have been very deeply interested in representation learning and how to improve representations by various mechanisms for the last, almost decade of my life. And this continues to, excite me. And right now, I'm going to present, particularly deep dive into a couple of papers that, me and my sort of colleagues in Amazon have been working together on. So the first one is called multimodal pre-training for automated speech recognition. And it's a joint work with my co-authors. And we talk about how we combine globally the sort of robust representations with local accurate representation. And the next one would be about how do we do this content versus context factorization for learning better representations, again for automated speech recognition. Now coming to the first one, we know that many of the automated speech recognition models, which are becoming more and more popular thanks to all the systems that we have, AI systems that we have, particularly so as a result of it, we know that it's important to first of all give a little bit of introduction into as to how these automated speech recognition models, what they're good at and what they can get help with. So, for example, ASM models, they focus on extracting phonemes from local waveform representations, and one of the things in which I would say that an ESR model has typically been working, in the literature is that it has a encoder and a decoder structure, but it also, this encoder and decoder are then jointly sort of trained, and that is what it's called the neural transducer architecture, or the RNT model, where the T stands for the RNN T and model. And so RNN is a normal RNN. It could be an NSTM. It could be a transformer, and the T is the transducer part, which is this joint training that you do here with RNT loss. And this is the other representation where you have a joint model, the RNT, as you see, and the RNT loss. And you see this, the waveform is going into feature extractor, into the encoder, and then you have this loss matrix that we're shown here. Now, in the encoder part of this RNT, is what we use. What we currently use is the conformer, and this conformer, uses self-attention like normal transformer models, but also of course has convolutions, to extract, because basically from the input spectrogram, does convolution or subsampling. And you can see this, expansion first, and then you have this conformer blocks. You can see the conformer blocks, how they look like. You have multi-headed self-attention, and that is the basis, for how we are, what we're using for learning, um, uh, based on this attention mechanism. Now, self-attention, is a very powerful, mechanism as we know it. But self-attention, after training is mostly local, as we see from this plot. Now, local first is good because, the models are less likely to hallucinate, and, it focuses on, what exactly matters. But what we also know that what local models miss out is that they're often not very context aware, and they often struggle to disambiguate, phonemes when there's global noise or in any other kind of global noise present. So we thought, what can we do? Now, what we know is that there's another model architecture, which is called Hubert, which has come up. And what the Hubert model does, effectively, is that it learns a better global, context, based representation. So what, as you see, from the waveform, we also see that, we basically cluster together, these, and as we create these clusters, which is called acoustic discovery, unit discovery system, which is basically through k-means you create these targets for this model in a basically unsupervised way. And the idea is that now, if you have any kind of bot-like structure, which basically extracts information from the waveform and then transforms it, using a transformer layer and masking, then you actually, try to then predict these targets that you've created by clustering. And that is called the Hubert architecture. Now, global context is good, first of all, because it tends to be more robust to noise, but also large amount of pre-training can really help models build strong statistical trials, for unseen data. So it helps to generalize better, as we know. But of course, the problem can be that, they can be prone to hallucination and will often also trust priors over local evidence. And also there's another problem that models often tend to encode low frequency info over high frequency signal due to this lossy target. Because remember that here, in this model, we don't actually have, actual labels, right? So we're generating sort of these pseudo targets through this clustering approach. And that's why, it can be noisy and can be lossy. But then we thought, how can we leverage now the strength of both the global and the local information in learning these audio representations? Well, we can cover a wide range of scenarios and alternate environments. First of all, that's what we need to do if you want to, build a good global context embedding. We want to encode as much semantic information as possible, and also generate representations that can give useful contextual information. So these are some of the properties that we want from a good global context embedding. Now, how do you do that? So we thought to build a good context, global context embedding, what we can do is that we can actually pre-train, we thought, using the kinetics data set. This kinetics is a popular data set in the video world because it is actually short, about 5-second videos, mostly in the action recognition genre, which are curated from the YouTube 8-minute data set. So what we thought was that, remembering that you have the standard ASR model where the encoder is a conformer, what we want to do is that we want to pre-train, using these kinetics data set. And that's a global context information. And the hypothesis is that if we actually pre-train using a video model, then it should help our local ASR task. And why is that intuition? Let's go to the results section and find out more. But I'll give you more intuition as to why we think, this was why in the beginning we thought that the hypothesis worked. Now, so to make this hypothesis work, what we did was we made an extension to the Hubert-like architecture, and we call that AV-BERT. So essentially, what you see here, you have still the audio-based Hubert that I talked about, but also you have now the AV-BERT, which means that because we have the fact that we have added, again, a video-based thing where it's now taking the visual input and similarly clustering them, also, and creating the pseudo, targets, and then essentially the BERT-like, model is actually effectively trying to predict those targets. But We also have something which is called, in the BERT model, we also use something called progressive masking. And together, that's our model. Now, how does it fit in? Well, we still have the base model conformer, but what we do here is we take this AV-BERT model that we have trained and we freeze it. And then this pre-trained encoder, right, is here in the blue. And then we have the normal, stack that we have for automated speech recognition, where I showed you that we have a standard conformer, it goes to self-attention and to the RNT joint model loss. Now the encoder part, in addition to the normal conformer stack, we have this AV-BERT encoder, added as a frozen model. And what we do is that we cross-attend, to that. And this is what you see, that we have built now a cross-attend, deep fusion cross-attention layer, and we cross-attend, to these embeddings, right? And that is how it works. And when we do this, we see that, in the Libre speech, we have, improvements, and also we have, improvements in our internal datasets as well. We particularly see that this is very helpful in long tail, which is very hard to, otherwise, do well on when you don't have enough training data. And that is one big benefit of this kind of pre-training approach. Now, before we get to the next one, so I want to mention what is the intuition, right, behind this model that we think that our hypothesis worked. Well, the idea is that, when you're saying in ASR, right, when you're trying to do automated speech recognition, suppose you say the word car, right? And the job is to figure out, okay, what did the user say? The word car, right? Now, the car can be said in many different accents, sometimes in many different languages. But, the visual representation here of a car, tells you what what a car should look like, what is the rough, attributes of the car that we usually see. And that doesn't change much from language to language or between accent to accent. So which means that if you actually during pre-training, you've seen the car, being associated with, various kinds of, scenes or even, descriptions of different contexts, that this kind of visual scene helps you distinguish in that context, the ASR word car, because you think that, okay, this is the user speaking in this context of, this word, car or something else. Now, that should help, of course, when we have also the vision coming in as a modality. But why does it help when even if we don't have vision coming as a modality during inference time, which can happen, right? And that is perfectly okay because the AV word encoder here is frozen. Well, it still helps because during pre-training time, it has learned to associate this word, sort of car, with, or the sounds of the word car with this, object, which looks like a car. And that probably adds an invariant to the data and can, sort of help generalize to other, scenarios, where you hear the word car in similar context. But most importantly, helps you distinguish from other kinds of, object classes like lamp, because a lamp looks very visually different. So no matter, what language you say, the lamp and car will always look different in the visual, space. And that is one of the fundamental reasons why we think that vision modality helps anchor, these, this language or speech-based, utterances. Now, coming to the next one, the content and context factorized representation of automated speech recognition. Here, what we talk about is that the other one issue with ASR, though, is that, there's often, background noise and, then there are multiple speakers, and sometimes, that can, sort of interfere with you understanding what the content of what the user is saying. Because in the ASR world, you're really more interested in the content of what the user is saying. And so what happens that if you can, in this case, think about how you can, factorize, right, the content, which is, let's say, what the user is saying, which is separate from where it's being said, or, and who is saying this, or background noise. So these we all sort of factor into context, right? And so for our talk purpose, we'll say content is what we are really interested in, and context is the background thing here, where we are trying to factorize out the noise or the other kinds of information, because we want to focus, on the content. And what is good? So these explicitly factored representations, they are good at reducing spurious correlations and can help improve generalization. They can be also difficult to train, of course, because they require tasks for each modeling. You have to basically factor in separately what you want to do, and then also can often reduce metric performance, as spurious correlations may give good results in some cases, right? So we are also eliminating those possibilities. But we thought, what is the best way? So how can we effectively separate context and content? So what we want, the properties again, is that you want to maximize the mutual information between the content representation and the correct ASR label. And also, you want to encourage the content representation to encode background feature, noise, and speaker identity, because that's where you want to club them together and separate out from the, the other representation that you want, right, that you're interested in. And also, we want to minimize the mutual information between content representation and context representation, right? And by the way, number 2 has a typo. It should be encourage the context representation to encode background features, noise, and speaker identity. Now, this is the proposed model that we have for that. So if you have the raw audio coming, right, and we have again the speech encoder, which in our case, remember, is the conformer. So now, how do we do that? So the content embedding network, we call, it's purple, and the context embedding network is pink. That's what we see here. Now, this has, so we have to train this, and in a sort of such that we can factorize the content and context and still run a very good representation overall for the ASR task. And we use here particularly 4 different kinds of losses. So we use reconstruction loss, context, contrastive learning, downstream ASR loss, and we also use here the cyclic, disentangling. What does this mean? Now, the downstream ASR loss is the loss we usually use for ASR, which is what I talked about earlier. Now, the additional things that we use is that the context contrastive learning. So what means is that in the context space, we do a contrastive learning, and we see that if something belongs in the same utterance, then it's positive example. Sorry, if it's in the different utterance, then it's a negative example. And that's how we define this context contrastive loss. Additionally, we also we have a cyclic reconstruction. What it means is that you actually don't want the content to predict the context and vice versa. So what do? You actually have this kind of structure where you actually define a gradient reversal layers, right? So basically you have a negative gradient on this when you're training. The other thing is reconstruction. Now you do this factorization, that's all very good. But then at the end of it, you still want to make sure that you have done a good job in, learning the representation, and when you're combining them, that, ultimately that, you're reconstructing, let's say, the signals back again, then it still is something meaningful. So with that, with this whole losses, and we of course did a weighted, combination of these losses, and then we get improvements on speech. And both these papers that I talked about are published in ICAS and InterSpeech respectively. And we also see, particularly, things improve. So what we see that Verder improved with both RNA and conformal models, and deletion significantly improved on our glide path models. Apart from that, we also have, we tried other ways of injecting noise, and what we see that once we, as expected, right, we're doing a better factorization. So as we keep increasing noise, in the environment, our performance, keeps getting better and better with our model over the baseline models. And the last thing I was mentioned that one of the things we also worked on recently is actually that we talked about this multimodal pre-training, right? And there we said that the videos have to be, we're using the SkyLead dataset where the audio and the video are supposed to be aligned. But sometimes what if you have the audio and the video are not aligned? Well, we talked about the fact we said that suppose you have different modalities, right? And what we can do is that suppose if you have video and you have text data, which are, not aligned, which can often happen. We want to use all of this to perhaps pre-train. How do we do that? So what we did was we showed that if you actually have, you can treat, basically you can use pre-trained single modality video and text model. Now, what is the trick that we use? That we use pseudo label. These are pseudo large video data set with image capturing models. And then we So basically that's what we do. And then we use pre-trained single modality models, freeze the pre-trained models and connect them with adapters, and then use both pseudo-label video caption and real image caption for adapter training. When we do this, we see that we are getting, as good result, right, as the state of the art, which shows that even if the audio and the video, or also in particular in this case, the video and the text are not aligned, we can still use them to jointly pre-train our model. And that is and these adapters are very powerful because this less gradient to store compute and has less parameters, reduces forgetting, and same as fine-tuning performance. And also this also has separable cross attention, which makes them more efficient. So now the key takeaways then from my presentation today is that self-supervised learning can be used to augment current local techniques with global representation. Multimodal representations can help even if only one mode is available at test time. Factoring content and context can help us to better model clean and noisy ASA data. Leveraging auxiliary losses for better factored learning can help lead to a more holistic model of ASA data. And it is possible to pre-train high-quality video models without any parallel video text data. So this is my talk today, and I'm happy, to take questions, sort of offline. And thank you, everyone. And there's some future work here as well. Thank you very much.